Hi, good morning all. Welcome back to our channel. Today we are going to solve problem number 41. This is under maximum power transfer theorem. Find the value of load resistor and obtain the maximum power transferred from source to load. Okay. So here a current source is given. So first we will find out VOC. Okay. So first step we'll find out VOC, and second step we'll find out RThevenin and we'll substitute in the formula. Okay, so first how to find out VOC is very important. Okay, so first remove the load resistor. Okay, remove the load resistor and find the voltage across this point, which is VOC. But before solving, you can see here this is like a practical current source. I am going to apply source transformation. Okay, so when I apply source transformation, let us assume I'm connected between node 1 and 0, and this is node 2 and 0, all are zeros. Okay, so now between 1 and 0 I'm going to reduce it, and I'm going to use source transformation. The value of this resistor is 10. Automatically here also you are going to get 10, and here you are going to get a voltage source where V is equal to I into R. The value of I is equal to 2 into 10, so which is nothing but we are going to have an 20 volt source. So this is a 20 volts source connected across a 5 ohm resistor and an battery, and we reach node 2. So this is what the reduction is. And between 2 and 0, and again a 2 ohm resistor is connected, and this is VOC, and we have to remove the load resistor, and we are connected with a battery of 10 volts here. Okay, this is plus and minus. So RL is removed. So now we want to find out VOC. Here this is VOC. This cannot be moved to point 2. Why? Because in between there is an voltage source. Now let us assume this node as a new node, and we'll label this node as some Vx. Okay. So now let's try to find out Vx. How to find out Vx is very simple. So let's try to mark the current is flowing from this point to this point as a current I1, and the current through this branch I am marking as I2. So therefore how many currents are there? Only two currents are there. Now let us try to apply nodal analysis. Okay, so apply nodal analysis at node Vx. There's nothing but applying Kirchhoff's current law at node Vx. So you can see here how many entering currents are there. No currents are entering, only leaving currents are there, which is I1 and I2. So 0 is equal to I1. How to write down the current I1? Current is leaving. This is nothing but plus Vx. So Vx, and again the current is leaving. This is of 6 volts. So current is leaving. What is the leaving polarity? Plus 6. Okay. Again the current is leaving. What is the leaving polarity? Minus 20 divided by R. What are the resistors connected? 5 and 10, which is nothing but 5 plus 10. So how to write down the current I2, which is flowing in this branch? Vx minus 0, Vx minus 0 divided by 2 ohm. So when you separate the terms, here we are going to get Vx by 15 plus 6 by 15 minus 20 by 15 plus Vx by 2. So send these terms to this side, then you are going to get minus 6 by 15 plus 20 by 15, that is equal to Vx. I am going to take common. When you take Vx as common, this is 1 by 15 plus 1 by 2. So from here I can successfully calculate the value of Vx. Use your calculator, then you can get this value. So therefore the Vx we are going to get it as 1.643 volts. But our target is not the value of Vx. Our target, so now after reducing, so here this is Vx, and this is the node VOC, and this is the resistor, and here we are having a small voltage of 10 volts. This is positive and negative. I want to link this VOC Vx as well as this 10. So in order to do this, let us try to apply Kirchhoff's voltage law inside the loop to link all the voltages. Let's try to assume the current is flowing like this. Whenever the current is flowing, so this is nothing but plus VOC, and this is nothing but current is leaving, or the leaving polarity, minus Vx, and current is flowing like this, which is nothing but minus 10. So we require the value of VOC. VOC is equal to Vx plus 10. Okay, already the value of Vx is 1.6 plus 10. So therefore the open circuit voltage what we require is 11.643 volts. Okay, and then we need to find out R Thevenin. So how to find the value of R Thevenin? So redraw the same circuit and replace the sources with the equivalent sources. So just copy it and I'm pasting here. So we need to find out R Thevenin. So how to find the value of R Thevenin is like this. Okay, so the value of R Thevenin is equal to, okay, so this source is open and we are having a 10 ohm resistor, and here we are having a 5 ohm resistor. This voltage source is short circuited, and here we are having a 2 ohm resistor, and we are short circuiting this source, and the load is open. So as soon as you remove the load resistor, the resistance seen from the open circuit terminals, we can calculate the value of RThevenin. So this is nothing but V is equal to 0. This is 2 ohm, this is short circuited, and this is open circuited. Now the current starts flowing, and the current flows into 5 ohm, and the same current will flow. The current will not divide in this branch, and the same current will be flowing. I can say now 10 and 15 are connected in series between the nodes 2 and 0. So now between 2 and 0, I'm having an 2 ohm resistor, and here I'm going to have only a single resistor, 10 and 15. 10 and 15 are connected in series. This is nothing but 10 plus 5, 15, and 2 ohm. And we need to find out the RThevenin here. And you can see here, once again the current is entering and current is dividing. I can say these two branches are connected in parallel. Okay, whenever they are connected in parallel, the formula is product of resistance divided by sum of resistance, which is we are going to get it as 1.76 ohms is the value of RThevenin. Okay, so successfully we had find the value of RThevenin. Very simple current source. Okay, we follow the concept of this RThevenin is, if you have a current source, deactivate this current source. The magnitude of the source is 2 amperes. Deactivating the source is indirectly making open circuited, and automatic current becomes 0. And this voltage source is there. This voltage source is of 6 volts. Deactivate this 6 volt source is indirectly making that voltage as 0. That's why this voltage source is short circuited, and this voltage source is also short circuited. And resistance seen from the open circuited load terminal will give us the value of RThevenin. Then just I applied this, these two are in series, and I have got true, and again these two are in parallel. So I got the value of 1.76. So VOC value is 11.64 whole square divided by 4 into RThevenin. So the value of RThevenin as I solved is 1.76. 1.76. Then do with your calculator. Then we can find out this value. This is 19 watts. 19 watts is the amount of power transferred from source to load. So how much amount of power is transferred? 19 watts of power is transferred from source, this source, and is delivered to the load. This is the amount of power transferred from the source to load. So if you want to devise, I'll just give a small overall view. So remove the load resistor, we'll get an VOC, and this VOC will not move to this point. Why? Because an voltage source is there. That's why we have to find out Vx. using nodal analysis. Find Vx using nodal analysis. Take this is one current and this is another branch current, and express current I is equal to V by R form as I expressed here, and find the value of Vx and link Vx, Voc and 10. Then we can find the value of Voc. And already I discussed how to find out RThevenin. So if you feel the content is useful to you, please give an like, share with your friends those who are studying the same subjects. If you have any doubts, let me know in the comment section. I can answer your doubts. And if you're watching the channel for the first time, subscribe to my channel with the name KV Tulsiram, which is a free channel, and kindly support this type of free channel for the betterment of students and faculty. So we'll meet in the next video. Yours obediently, Ram.